This is B. Naresh, working as assistant professor in EC department. And today's topic is problems on Clipper circuits here. So in the previous sessions, we analyzed the Clipper circuit analysis here. So in this session, we are going to discuss the problems on this Clipper circuits here. So first, we'll see the one problem. So for the diode clipping circuit shown in below, assume so VR is a 10 volts and a VA is a 20 sine omega t and diode forward resistance is 100 ohms and a reverse resistance is infinite and V gamma is a 0. Draw to scale the input and output waveforms and label the minimum and maximum values if the resistance is 100 ohms and the resistance is 1 kilo ohms and the resistance is 10 kilo ohms here. So this is the given circuit here. So for this given circuit, we need to find out the output voltages here with respect to clipping circuit analysis here. So here it is acts as a positive P clipper with respect to some reference voltage and this is VR. So here this reference voltage here represented as your 10 volts and the input signal is represented as 20 sine omega t. And in this problem, again, we need to consider a diode. So when the diode is conducting, it offers a forward resistance and here that forward resistance is represented as your 100 ohms. And in this problem, given the reverse resistance of this diode is represented as your infinite and the cutting voltage of this diode is represented as your 0. So with respect to all these parameters, we need to identify the output voltages with respect to this given R resistance in the different resistances conditions here. So one time we need to choose the resistance is 100 ohms and another time we need to consider 1 kilo ohm and another time we need to consider the resistance is 10 kilo ohms. Means this resistance we need to replace with 100 ohms, 1 kilo ohms and your 10 kilo ohms. And here this VA is represented as 20 sine omega t and the reference voltage is represented as your 10 volts here. When the diode is conducting, we need to consider the diode resistance is that is your 100 ohms here. Now we'll see the analysis with respect to this given circuit here. So coming to the solution, let us assume that, so if you observe this circuit diagram and in this diode and here it is represented as anode and here it is represented as your cathode and the cathode is connected to your reference voltage that is your 10 volts. So first we need to identify that at which condition the diode is conducting, at which condition the diode is not conducting. And by using these two instances here, we need to identify the output voltage with respect to your given resistance values here. And based on the clipping circuits analysis, we know that if the anode voltage must be greater than or equal to cathode voltage, so the anode voltage must be greater than or equal to cathode voltage, then only diode is conducting here. Otherwise, diode is enters into the non-conducting state here. If the diode is conducting, then we need to consider the equivalent circuit. So, and we know that if the diode is conducting, that equivalent circuit is represented as a resistance along with your current voltage. So, this is V gamma and this is a diode forward resistance here. And this is a diode equivalent circuit when the diode is conducting here. So in this case, they given that in a problem, they mentioned the diode forward resistance, this RF is 100 ohms and a V gamma is represented as 0. So hence, and based on this, we need to redraw this equivalent diode circuit. So when the voltage source is 0, that should be replaced with a short circuit. Hence, I'm going to redraw that circuit with respect to the cut-in voltage is 0. So if the cut-in voltage is a 0, that voltage source is replaced with your short circuit. So hence this is your short circuit here, and here it is represented as your RF. So when we need to consider this as a short circuit, so in the problem they mentioned that the cut-in voltage of the diode is 0. So that is the reason. Here I replaced this V gamma with a short circuit along with some a diode forward resistance, that is represented as your RF. So based on this analysis, if you want to make this diode is a conducting, we need to apply a larger voltage compared with your cathode voltage. And from this problem statement, here this cathode is connected with a reference voltage, that is 10 volts. Hence, at least we need to apply a greater than of 10 volts, then we can say that diode is in a conducting state. Otherwise, diode is your non-conducting state. So hence, here I am going to consider the two instances here. So what happens if the applied input voltage is less than of 10 volts, and what happens if the applied input voltage is greater than of 10 volts or greater than or equal to 10 volts. So first we will see what happens if the applied input voltage is less than of 10 volts. So in this case, so if you observe this again, the circuit here, and the first condition I consider if the Vi is less than of 10 volts. So when the input signal is less than of your 10 volts, that lesser voltage here passing through the anode of this diode D with respect to this cathode voltage, the cathode is connected to your 10 volts. Under this condition, so what happens here? Diode becomes to your reverse bias. Hence, the diode is in a non-conducting state. That state here, it is represented as your off state. So hence, I represented this point when the Vi is less than 10 volts, and according to your given circuit, the given diode is acts as a reverse bias here. Hence, and now I'm going to redraw the equivalent circuit. So how we are going to redraw the equivalent circuit? So if the diode is conducting, so we are on the two options. If the diode is conducting, it should be replaced with your a diode forward resistance along with your cut-in voltage. So this is diode is forward bias. If the diode is a reverse bias, ideally I consider that, and it is replaced with a simply open circuit here. So here this is diode state is represented as your off state. So that is the reason, based on your given circuit and with respect to your our applied input voltage, and whenever the input signal is less than of your 10 volts, and based on this condition, the given diode is enters into the reverse bias condition. That is the reason the diode is acts as your non-conducting state here. And that non-conducting state is represented as your off state. It is replaced with your open circuit. So hence, here I am going to redraw this equivalent circuit. So here I consider this point, I consider that the diode, and here the diode is replaced with open circuit here. So this point I represented as your diode is non-conducting state. Why? Because of that, under this input condition, your diode is acts under the reverse bias condition. Hence, it is replaced with a open circuit. Why it is an open circuit means, under the reverse bias, it offers the reverse resistance. And in the problem statement, they mentioned that the reverse resistance is infinite. So the reverse resistance is infinite means the current flowing across the diode is zero. So that I represented as this one. It's clear. So hence, so here diode is replaced with your open circuit, and in this point is your reference voltage, and here we consider that the reference voltage is your 10 volts here. The reference voltage is represented as your 10 volts. Now, and at this note, now we are going to observe what is the output voltage with respect to this equivalent circuit. So what is the output voltage now? This V naught is directly proportional to your VI signal. Hence, I represented this one. So whenever your applied input voltage is less than of your 10 volts, the output is approximately equal to your given input signal here, that is your VI. Now we'll see what happens if the applied input voltage is greater than or equal to 10 volts. So based on this given circuit, if you observe this the given statement, and at this point, so what we are doing now, the second condition, what we are taking, your applied input voltage is greater than or equal to 10 volts. Means the maximum larger voltage is passing through this anode of the diode with respect to your cathode here. Hence, at this point, what happens here, it satisfies this condition. So what is the condition here? Anode voltage is greater than or equal to your cathode voltage. And under this point, diode is enter into the forward bias mode here. If the diode is enters into the forward bias mode, the state is represented as your conducting state here. So that conducting state is represented as your on state. So based on this analysis, now we are going to redraw this equivalent circuit under the applied input voltage is greater than or equal to 10 volts here. So hence, I'm going to redraw that equivalent circuit. So means, so which one we need to replace here? The diode should be replaced with your equivalent model under the forward bias mode here. So hence, here I represented this one. So this point here, this is the diode. So actually, we know that when the diode is forward bias, it is replaced with the equivalent circuit is diode contains a diode forward resistance along with cut-in voltage. Here this is V gamma and this is a diode forward resistance is RF. But in our problem, they mentioned that the cut-in voltage of the diode is 0. So if the cut-in voltage of the diode is 0, means what happens here? This here, at this point, the V gamma is 0. So if the V gamma is 0, what happens here? So voltage source is 0 means if the any particular voltage source is 0, that should be represented as your short circuit model. Hence, I'm going to redraw this model. So this is RF. And now this V gamma is 0 means this V gamma is the voltage source is replaced with a short circuit. And this is RF. So this model, this equivalent model, here I placed here. So hence, based on a given problem statement, when the diode is a forward bias or a conducting state, and that diode is replaced with equivalent circuit along with the diode forward resistance here. So hence, here I represented this is RF and this is the reference voltage, and in a problem we mentioned that the reference voltage of the keeper circuit is 10 volts. Now we need to analyze the output voltage with respect to this equivalent circuit under the input voltage is greater than or equal to your 10 volts here. Now we'll see first, and for this circuit, first we need to identify the output voltage, the mathematical analysis here. So for this case, here I'm going to apply the KVL analysis. So we can apply the KVL. So what happens here means we need to write the VI. So here what happens, which current is the flows? The current is the flows I. Let us assume that the current flowing across this network, here I represented as your I. Now we need to write down the KVL analysis here. So for this case, now we can apply the VI is equal to, so this is I considered first, this is the VI, and this VI is equal to the voltage drop across this resistance along with the voltage drop across this RF and the voltage drop across this reference voltage. So hence I'm going to write like this, VI is equal to the voltage drop across the R and the voltage drop across the RF resistance and your reference voltage is your VRE. So, and now we need to calculate how much voltage drop is flowing across this resistance here. So this R means this across this resistance, which current is flowing here? I is flowing here. So hence we know that generally V is a product of current and your resistance. So hence I'm going to write this VR is represented as I into R. Similarly, the voltage drop across this diode forward resistance. So here also across this RF also the same current flowing, that is represented as your I. So hence the voltage drop across this diode forward resistance is represented as I into RF along with your reference voltage is your VR. Now you can simplify here. So your I is the common. Just you can take that I is a common. So means what happens here in this relation? So VI is equal to your I into R plus I into RF plus your VR. If I take in the I is a common here, this is R plus RF plus your VR. Now we required I here. So I is equal to what happened? VI minus this I taken outside, divided by R plus your RF. So that is the reason. Here I represented from this relation. I find out this I here. So I means it is a ratio of the potential difference between applied input voltage and the given reference voltage to the your internal input, the input resistance along with your diode resistance here. Now again, so from this circuit, we need to find out, so from this given circuit, we need to find out this output voltage. So along based on this circuit, what is the output voltage here? The output voltage here, it is represented as, so means this V0 is directly proportional to this node here. So here this V0 is directly proportional to this node. Hence, and from this model, here I am writing this output voltage. So along with the voltage drop across this resistance and along with this reference voltage is your VR. So across this resistance, the current is flowing. The current here it is represented as your I. Hence, I represented the output voltage from the circuit. V0 is represented as the voltage drop across this RF. I represented as I into RF. And along with the given reference voltage is your VR here. So this is the expression. But here, what is the I here? I is represented as, it is a ratio of the potential difference between applied input voltage and your reference voltage to the R and your R plus here, RF here. So by using these two mathematical relations, now we are going to find out how much output voltages or generates with respect to the given input resistance R. So here I substitute this I value. So what happens here if you substitute I value? So then the V0 becomes to your Vi minus VR divided by R plus RF into RF plus your VR. So by using this mathematical relation, now we are going to calculate the output voltages here. So under this condition, so already we observed if the input voltage is less than 10, what happened? If the input voltage is less than 10, output is always proportional to your given input signal. Now we'll see what happens if the input voltage is greater than or equal to 10 volts. At this point, now we need to substitute this R value, different cases here. So in the problem, they ask the different resistances values here. So the first time, I'm going to assume, so R is equal to 100 ohms here. And now we need to substitute the values, and we know this input voltage, and VR means your reference voltage. The reference voltage they given the 10 volts. R we need to change. So the first time we need to assume the R is 100 ohms, and RF is they given that 100 ohms, and again VR is your 10 volts. Now here I'm going to substitute this one. So your VI is so they represented as VI is 20 sine omega t. So that is the reason. So here I'm representing that the peak voltage is 20 Vi, and the reference voltage is a 10. R, I consider this is 100 ohms. And RF means in a problem, the diode forward resistance they given that 100 ohms. And again RF is 100 plus your reference voltage is your 10. Then simplify this ratio. It gives the output voltage V0 is 15 volts at R is equal to 100 ohms. Similarly, we need to calculate how much voltage drop it generates if R is a changes. So that is the reason. In a second case, if I assume this R is equal to 1 kilo ohms, now how much voltage drop is generates across this clipping circuit? So hence, I am going to substitute this R is a 1 kilo ohm here, and the remaining parameters are same. Input voltage and the reference voltage and diode forward resistances are same. Only thing is we need to modify this, the input resistance R. So this time here we are going to consider this R is the 1 kilo ohm here. So hence here I am going to substitute where VI is a 20 volts, VR is a 10 volts, and here this is R 1000 ohms and RF is 100 ohms. Again this is RF is 100 plus 10. Then simplify this ratio, it gives that V0 is equal to 10.9 volts if R is equal to your 1 kilo ohm here. Now similarly, now we need to analyze what happens if R is 10 kilo ohms here. So in the third case, here I am going to assume if R is 10 kilo ohms, now we need to identify the output voltage. Again substitute all the values in this mathematical relation and output relation. So this is the output relation. So now I'm going to substitute this output voltage here. So where VA is again 20, VR is a 10, but R is replaced with the 10 kilo ohms. So hence I mentioned the 10,000 plus RF they given that 100 ohms and again RF is 100 ohms plus your reference voltage is 10. Then simplify this one, then it gives that the V0 is 10.1 volts if R is equal to 10 kilo ohms here. So these are the different output voltages with respect to your R is changes here. Now we need to plot the response. So for this case, and let us take, if I consider this is my input signal. So what is the input signal? This dashed line I represented with the input signal. And they given that Vi is 20 sine omega t, means this peak voltage is 20 and again this peak voltage is 20. Now we need to reference in a given circuit, they given that the reference voltage is 10 volts, means first we need to locate the reference voltage. And in the problem, the given reference voltage is positive reference voltage. So hence, I'm going to first fix the reference voltage. So means in a positive peak, I'm going to mention the reference point. So this is the 0, this is 20, and 10 means suppose the center point. Let us take this is, I consider the 10 volts and this node I represented as a VR. Now we need to analyze. So this is based on this reference point and we are having the two portions. This is the first portion and from this point to this point, this is the second portion. If you observe this first portion, what happens here? The first portion is Vi is greater than of 10 volts or greater than or equal to 10 volts. But second portion is Vi is less than 10 volts. So this portion is Vi is less than 10 volts. And this portion is from this point to this VR 10 volts to VM 20 volts. The portion we can represent that is Vi is greater than or equal to 10 volts. Now we need to analyze we need to draw the output voltages. Already we observed these two conditions here. And we observe that the input voltage is less than of 10 volts. What happens here? So in the first case, we observe Vi is less than 10 volts. The output is approximately equal to your input signal. means that the output is linearly changes with respect to your input signal. So that is the reason, and this is the condition when the your input voltage is less than of your 10 volts. Now we'll see what happens if the VI is greater than 10 volts or greater than or equal to 10 volts. Under this point, we observe the three cases. One is R is 100 ohms. One is we observed R is a 1 kilo ohm. One is we observed R is a 10 kilo ohm. If you observe this one, if R is 100 ohms, what is the output voltage? That is 15 volts here. Now we need to locate that one. So in this case, so if VA is greater than 10 volts, if R is 100 ohms, that is the 10 volts, 15 volts means. So let us take this is constant. Let us take this point, I consider that 15 volts. And this is a condition for if R is equal to 100 ohms here. Similarly, we need to identify if R is a 1 kilo ohms, we observe that V0 is 10.9 volts means let us take this is 10.9. So and this is the condition for if R is 1 kilo ohm. And similarly, we also observe that if R is the 10 kilo ohms, output voltage is 10.1 volts means is very nearer to this 10 volts. So this point here I consider that 10.1 volts, and this is if R is equal to 10 kilo. So like this, we need to plot the graph with respect to your given input signal. Now we'll see another problem. So for this clipper circuit shown in below figure, the input is 60 sine omega t. Determine the output voltage here. For the given this clipper circuit, we need to find out the output voltage with the given input signal is 60 sine omega t. So here, if you observe this circuit, the given circuit, where are the two diodes, and those are represented with D1 and D2. And the D2 of cathode, this is the D2 of cathode, and this is the D2 of anode. The D2 of cathode is connected with some reference voltage. That reference voltage is 15 volts here. So means that if you want to conduct this D2 diode, the anode voltage must be greater than or equal to this 15 volts. Then only the diode D2 is enters into the forward bias mode or enters into the conducting mode here. Otherwise, the diode is in a this diode D2 is in a non-conducting state. But coming to this D1 diode, the D1 of anode, this is the D1 of anode and this is the D1 of cathode. The D1 of anode is directly connected to your input source, means that so if the input is greater than of 0, then diode D1 is enters into the conducting state here. So based on these 2 points, now we are going to analyze the output voltage with respect to your given input signal, that is 60 sine omega t. So in the first case, then coming to the solution, and here let us assume that what happens when your applied input voltage is less than 0. So at this point, we are going to assume that the applied input voltage is less than 0. If the input voltage is less than 0 means the negative portion of your given input signal is passing through D1 of anode, and similarly, so here also let us assume that a lesser voltage is connected to D2 of anode. So what we discussed, what we analyzed from this circuit here. So if you want to conduct this D1 diode, at least the applied input voltage should be greater than 0. And if you want to conduct this D2 diode, your anode voltage must be greater than or equal to your 15 volts. Then only those diodes will be a conducting state here. So hence, and based on this approaching, what we are approaching here, your applied input voltage is less than 0. Under this approaching, we are analyzing that. So what happens, your anode voltage is less than of 0, hence D1 is in a non-conducting state. Similarly, D2 is also your non-conducting state. That is the reason. Both the diodes D1 and D2 are enters into the reverse bias mode. That is nothing but your off state here. So hence, here I represented as under this condition D1 and D2, the states are represented as your off state. So if both the diodes are off state, I'm going to redraw the equivalent circuit. So this is the actual given circuit. And with respect to this assumption, when the input is less than 0, and we made that both the diodes means D1 and D2 are enters into the non-conducting state. Hence, so here this D1 portion is represented as off state, and at this point the D2 is also represented as your off state here. And this is the equivalent circuit. Under this equivalent circuit, so what happens here? Here the current is not flowing in this network. Why? Because of that. So here the D1 is off state and D2 is off state, hence the output voltage here it is represented as 0. So that is the reason the output voltage here is represented as 0. Now we'll see what happens if when VA is greater than 0 and VA is less than 50, means your input is lies between 0 to 15 volts. For this given circuit, your now input is lies between 0 to 15. So what we need to assume, so here it is a greater than 0 means positive voltage is passing through your D1 of anode. Hence, D1 is becomes to your conducting state. But that should be less than of your 15 volts, but your input should be less than of your 15 volts. So means anode, if the less than 15 volts across this D2, this is anode and this is the cathode. So your cathode is made with the 15 volts here, but anode is voltage is less than of your 15 volts. Hence, so what happens here? The diode D2 is enters again non-conducting state. So under this condition, so what happens in the diode's function here? D1 is acts as a conducting state and D2 is acts as a non-conducting state. Hence, D1 is represented as your on state, D2 is represented as your off state. So I represented like this. D1 is on, D2 is off under this condition. Now we'll see what happens in the equivalent circuit. So now the diode D1 is represented by on, means it is ideal I considered here. So here both the diodes I'm assumed as ideal diodes. So ideal diodes means if the diode is a forward bias, that is simply is replaced with a short circuit. If the diode is a reverse bias, ideally it is simply replaced with your open circuit. Hence, and here D1 is replaced with a short circuit, and this D2 is replaced with your open circuit here. And now we need to calculate how much voltage it generates here. So by using this circuit, now what happens? Your current is flowing like this. Let us take this is I. So now we are going to calculate this output voltage across this node. So this V0 is directly proportional to this resistance, means we need to calculate how much voltage drop is flowing through this 20 kilo ohms resistor. So hence, that is the reason from this circuit, I represented that the V0 is equal to the current flowing across this resistance, means or the voltage drop across this resistance. That voltage drop across this 20 kilo ohms resistance is represented as I into your 20K. Now we need to calculate how much current is flowing with respect to this given input signal. So hence, now I'm going to determine this I. So how to find out this I here? So means I is in this network, I is nothing but it is a ratio of voltage to the resistance. So which voltage drop here? The voltage is Vi, and the resistance means we need to consider the total resistance, the current flowing through this 20 kilo ohms along with this 20 kilo ohms here. That is the reason. The total resistance is represented as 20k plus 20k. Now we need to replay this I value here. Hence, the V naught is, what is the V naught here? So V naught is I into your 20k. So here I represented this. The output voltage V naught is equal to Vi by 20k plus 20k into your 20k. So this is the output voltage when the input is lies between 0 and your 15 volts here. If it is a less than 0, output voltage is a 0. If the input voltage is a lies between 0 and 15, the output is represented as this one. Now, let's take what happens. For this simplification, this 20k, 20k, 40k, and this now I can simplify this one. Now this output is one half of the given input voltage here. Under this condition, the output voltage is represented as half of the given input voltage. So hence here I represented that the V naught is half of the input voltage. So similarly, now we need to identify again for the same circuit what happens if the Vi is greater than of 10 volts. So up to this point we observe that what happens if the Vi is less than 0 and your input is lies between 0 to 15. Now we'll see what happens if the input is greater than 15 volts here. Now you can observe in this circuit, if the input is greater than 15 volts means the 15 volts is passing through this D1 of anode. Similarly, the larger voltage is again passing through your anode of D2. So from this point, what happens here, both the diodes are enters into the forward bias mode. Hence, both the diodes are acts as your conducting state here. And those conducting state, here it is represented as your on state. D1 and your D2 is on state. So hence, here I represented that under this condition, we observe that both the diodes are your on state. D1 is on and D2 is your on state. Now we need to redraw this equivalent circuit under this condition. So means, again here I assume that both the diodes are ideal. Hence, D1 is represented as short circuit. And again this node D2 is also represented as your short circuit. At this point, now we are going to calculate the output voltage. Under this equivalent circuit, now this V naught is directly proportional to this node voltage. Directly proportional to this node voltage. So hence, what happens here at this point, directly that is equal to your 15 volts here. So from the circuit, so V naught is directly proportional to this VR. Hence, that is equal to your 15 volts here. So that is the reason we observe the three conditions here based on a given circuit. So the first what we observed here, when Vi is less than 0, we observe that output voltage is 0. The second point, the Vi is lies between, so Vi is greater than 0 and Vi is less than 15 volts. We observe that V naught is equal to your Vi by half of the given input voltage. And the third case, we observe that when Vi is greater than 15 volts, we find out that V naught is equal to your given reference voltage, that is equal to your 15 volts here. So up to this point, we discuss some of the problems on a Flickr circuits here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.